Okay, second method that we're going to talk about here is called Heinz method. Heinz method is really similar to Euler's, but it starts involving something called predictor and corrector steps. So if we follow kind of the steps for evaluating here, the first step is first we'll take a predictor step. Okay, and then second, we're going to take a corrector step. Corrector step. Okay, so what are those things? Well, so first my predictor step is going to be, I want to predict what I think the temperature is going to be. So I'm going to follow first Euler's method, and I'm going to predict what I think the temperature is going to be at the next time step. So that would be Tj plus 1 is equal to Tj plus dt dt. Evaluated at T equals Tj and time equals time j times delta T. Don't forget that. Okay, so that's predictor step. But actually what I want to do is I want to take this step forward, get my temperature at Tj plus 1. Right, so now I'm up here, and I'm going to then reevaluate the derivative at T equals Tj plus 1. So step forward, evaluate the derivative again at that point, and then bring those two things back together and take the average of them and step forward. So actually, let's designate this, our predictor step here, as T hat. Okay, so I have this like T hat. It's kind of a temporary T that I'm going to use. It's not the actual T that I finally step forward with. Okay, so T hat is our prediction, and then our corrector step is going to be T at j plus 1 is equal to Tj plus dt dt. Evaluated at, I'll just write it this way, Tj and time j, plus the evaluation of this derivative at T hat j plus 1 and time j plus 1. Okay. Take the average of that and multiply by the time step. So I would need to go back and do Heinz method again at the next step, right? So you're kind of stepping forward twice, coming back, average together. You kind of sketch out what it looks like. So first I'll say I'll take some step like this. This becomes my T hat at j plus 1. Right? I'm going to evaluate again and find the derivative. Maybe it looks like this. And so that would be this derivative over here. And then I come back and I'm going to take the average of this guy and step forward. Okay, so it's not, I didn't draw it very well as an average, but maybe you get the idea. So you take the average and then we step to our next temperature. Okay, so what's the advantage of this? Well, we're actually now evaluating the error, or we're evaluating the derivative twice, right? So this becomes actually a second order technique, which means that it's going to reduce our error. Because how does that actually play out? Let's do kind of the equivalent stats here. So for, excuse me, for m equals 11, delta T equals 0.04 seconds. That leads to a global error of 1 degree Kelvin. Okay, right, last time we already said 8.5 Kelvin for Euler. So just by doing this evaluation twice, second order evaluation, now we've significantly reduced our error almost by an order of magnitude. Okay. Now if we look at m equals, let's say 101 with a delta T of 0.04 seconds, let's see, the error here is 0.01 Kelvin. Okay, so that's actually 2 orders of magnitude lower than our top case, and what, 3 orders of magnitude lower than the Euler's method for the same number of steps. Okay, so this kind of implies that our global error is proportional to delta T squared. Okay. This will be fun to listen to on the recording. All right, so global error is proportional to delta T squared. And again, we could write out the expansion for this and I could kind of prove it out, but I think it's sort of clear what's happening, right? We have two evaluations of the derivative. That gives us a second order problem, and we can move forward with that. So just one minor point here. So let's actually do the global error calculation. Okay, so global error is, again, approximately equal to the sum of local, which is approximately, for this, it's going to be m times k. That we should call that something else, but k is our evaluation of the derivatives, times delta t cubed, right? That's our local error. So that's implying we're taking the first and second terms in the expansion now, effectively, and throwing away everything else. Okay, so delta t cubed, and then this is actually the same thing as t sim over delta t times our k times delta t cubed, which is proportional to delta t squared. So that's kind of how that works. All right. So actually, how does this play out in terms of, sorry, John, go ahead.
So that second delta t is at 0.004.
Oh yeah, sorry about that. 0.004. Yep. Yeah. Yeah, that's a great question. Actually, that was the next point I had here. So let's talk through that. So for let's compare a Heun's method or Heinz method and Euler's method. Okay, so for a Heinz method, if you take 100 steps, or 101 steps, that's actually 100 times 2 evaluations. So 200 evaluations is exactly what you say. Let's see, for Euler's method, we would just take 100 evaluations. So what is, if we were to, let's see. So I have it framed slightly different here. So 100 steps led to 0.7 degree Kelvin accuracy, which we saw before. So actually, in order to get the same level of accuracy, we would need to have, let's see, 7,000 steps. Okay, so 7,000 steps compared to 200. It's 200. So that's not very clear what I'm writing, but so 200 versus 7,000 is kind of the number of calculations that we would need for each of the two methods. So in fact, for this setup, a Heinz is 35 times faster. So 35 times less computation for Heinz method. Okay. All right, let's keep moving here. So there's some other ones that you probably haven't heard of now. These are kind of slightly different. So this method is called Runga-Kutta. So Runga-Kutta is another numerical technique. It's a way of stepping forward in time, but it involves, instead of two approximations of the derivative, it involves 4 approximations of the derivative. So how does this work? Well, again, we're going to start with our temperature Tj. And the first thing we're going to do is we are going to I'll just kind of sketch it. So let's say we want to step forward. We're going to step forward halfway. Okay. So let's call this here, this is T at J plus 1/2. So that's halfway between the two nodes. Step forward halfway. And we'll call this slope here. We're going to call this AA for lack of a better term. It's just a single variable name. We'll call that AA. That's that slope. Okay, then at this point here, we've got some temperature T hat at J plus 1/2. Okay. So we've got an estimate so far of what we think one of the slopes is going to be moving forward. Okay. The next thing we're going to do is we're going to take an evaluation of this slope at this new temperature that we just calculated at T hat. Okay, so let's evaluate what we think the slope's going to be here, right? So AA was our first evaluation of what we thought the slope was going to be. This now is a second evaluation. We'll call this BB. Right? So now it's a second evaluation of the slope. So now we go back and we take that slope and we step forward again, okay, from our initial temperature. So again, this is BB here. And then we'll call this new temperature that we predicted T double hat. So T double hat, J plus 1/2. Okay, so now we have two evaluations. Let's see. Let's say we then evaluate the slope here now again. So let's call this evaluate. I'll do it in blue. So this is now CC. Okay, then we come back here to our initial step, and we step all the way forward on that slope. There's CC. This now, this position over here is now T hat at J plus 1. So when you've got T hat at J plus 1/2, T double hat at J plus 1/2, T hat at J plus 1. 3 different temperatures, okay, and 3 different slopes. And the last thing is let's evaluate, I'm running out of colors here. So I'll make a dotted line. So let's say we evaluate again at this new point, the slope, and we'll call this D. Okay, so we have 4 evaluations of the slope. All right, this is confusing, I get it, and you probably just want to follow the recipe and you go look in the book to do this. Let's actually write out the steps real quick. So AA is dt, d time at T J, time J. That was our first one. BB is going to be equal to, oh, sorry, let me do it this way. Okay, so then we evaluate the temperature at Tj equals 1/2. So that's T hat at J plus 1/2 is equal to Tj plus AA times delta T over 2, right? That AA is our derivative. Okay, and then from that we can calculate then the slope at that new temperature, which we call BB. Okay, so BB is equal to dt at T hat J plus 1/2 and time J plus 1/2. Okay, right, and then we use that to get our T double hat. So T double hat at J plus 1/2 is equal to Tj plus BB times delta T over 2. Okay, and then we use that to get our CC. Okay, so this is like super laborious. dt time. Now this is at T double hat J plus 1/2. Tj plus 1/2. Okay, and then the last thing was we went back and predicted T hat at J plus 1, the full step. Tj plus Cc times dt. Oops, sorry. Cc times delta T. Right. And note it's delta T over 2 for the half steps and the full delta T for this full step. Okay, and then from that last step, we said our slope at that prediction was dt, d time, evaluated at T hat J plus 1, time J plus 1. Okay. And then the last thing to bring this all together, our actual step is going to be Tj plus 1 equals Tj plus AA plus 2BB plus 2CC plus DD times delta T divided by 6. Okay. So there's some arbitrariness here, right? We're kind of weighting the BB and CC steps as more important. AA and DD is less important. But ultimately, it all has to work out to take a single step. Right? So that's how the Runga-Kutta method works. Let's see. So we have 4 minutes left. I think what we'll do, I'll just show you the code. There's a couple more methods that we'll get to. I think we'll get to them next time. But I want to start showing you the code for this. So let's look at Matlab real quick here. So in Matlab, what I've done is I've taken the analytical function, wrote that in here just as a point of reference. So this is the analytical solution we came up with. All of our constants all evaluated out. And then I've got the T infinity as a function of time as well. Okay, so the first one we did was Euler's method, right? We just come in here, enter our problem information. Here we're setting up our time array, same way we talked about. We say j minus 1 over m minus 1 times the simulation time. And then here's our time step. And then here's the actual Euler's method. So we're saying T at j plus 1 is equal to the current temperature Tj plus our evaluation of the state equation. Right? This is our evaluation of the state equation at time j and at t, at temperature j. That's our evaluation of it. Okay, so that's all there is to it. And then you just plot it or run it, and we'll plot it and we'll look at the solution. So here we have our t infinity function. Here on the red dots, we have our numerical solution, the one we just talked about, and then the green dots are, or the green line, which is almost impossible to see, is the analytical solution. Okay, so that was for, let's see, for 101 nodes. Let's actually do this for 11 nodes just to see how it works. Okay, so you can see if you don't choose enough nodes, you're starting to get some significant error. Right. So this was for Euler's method, I believe. Euler's method. So now let's look at Heinz method. Heinz method's the same thing, except now we're taking that t hat, right, our predictor step, which is the same as Euler's step, but it's just a predictor, and then we come back and average, use that to evaluate that derivative again. So this is the evaluation of that derivative a second time. Here's the evaluation of the derivative the first time, and then you take the average of those two slopes. Right, so now let's plot this for, let's see, how many nodes do I have? 11. So let's look at this one for 11 nodes. Okay, so that one for 11 nodes is actually a lot better, right? The error is a lot better. Okay, so almost with 11 nodes, we could get away with it, whereas for Euler's method, we couldn't get away with it for that. Let's see which one else. Here's the Runga-Kutta, the last one we talked about. So Runga-Kutta, same setup, same discretization. But now you'll see in my time and temperature loop, I'm evaluating these steps each time, right? I'm recycling the same t hat a bunch of times. Like if you don't have, once you use it to make the next calculation, you can kind of discard it. So we keep calling it the same thing, but it's being assigned to different values for each evaluation. Okay, and then we come back and take our step by averaging them by the 6th power. So let's see here. This is for, let's do it for 11 steps again. Okay. So here we're almost perfect, right? With our, just zoom in, we're almost perfect, or pretty much are perfect on the solution for 11 steps. So that additional evaluation for the Runga-Kutta method is really helping us quite a bit. Okay, so let's leave it there. We'll talk about the rest of the numerical methods on Friday.